All right, hello and welcome to this webinar on the new CLT features in FEM-Design 19. I hope you all can hear me and see my screen. And my name is Joachim Karlberg, and I work with customer relations and technical sales in Gothenburg, Sweden. With me today is Zoltan Bocskai from Budapest, Hungary, and he's the responsible developer behind the new CLT module. So if you have any questions during the presentation, you can submit them through the questions pane of the GoToWebinar panel. It should look something like this, depending on the version you're on. So submit your questions through there and Zoltan will answer as many of them as time allows during the presentation. Then after the presentation, we will have some extra time to go through your questions that need further explanation. So if you find that your question has not been answered, we will get back to you after the webinar. Okay, so the agenda for this webinar. After this introduction, we'll begin with a brief look at the theory background and the calculation methods. Then we will go to the input data and walk through how the tool works and explain what the different parameters are. Then we'll look at the analysis results and the stress results and the tools that helps us out with analyzing those stresses. Lastly, we'll finish off with the design check capabilities before we'll go through any remaining questions. Right. So we'll begin with a brief theory background, nothing too technical, just to get familiar with the principal theories. So first off, I'll mention that there are some limitations in the timber Eurocode. CLT is still not an individual material, and when it comes to calculation methods relevant for CLT design, they're based on beam theory, which would be too simplified to use in FEM-Design, since we can model plates with arbitrary shapes. So there are other alternative methods used in other CLT handbooks, but most of them are also too simplified and limited for effective use in FEM-Design. So the selected theory behind the CLT module is the laminated shell theory. It's also referred to as the equivalent single layer method in some literature. In general, it's usable to check the correct deformations and stress distribution layer by layer of a composite shell. The main advantage of this method is that with a slightly increased calculation time for the element stiffness matrix. Okay, the webinar is full now. Okay, I got the message of that. All right. Perfect. So if you have any colleagues that trying to connect now, they can't because we reached the maximum number of attendees. But we are recording this so you can see it after the webinar. Okay. So where were we? Yeah. Okay. This messages keep popping up. Okay. So, all right. Yeah, the main advantage of this method is that with a slightly increased calculation time for the element stiffness matrix using a homogenization procedure, the same number of equations remains in the final structural equation system, regardless of the number of layers. So another advantage is that this method allows for arbitrary geometries of shell regions and boundary conditions with additional solid shell and bar elements, because this way the degrees of freedom are compatible to each other. So in addition to this, we also needed a new finite element formulation. And the tricky part of that is the coupling effect between the bending and the membrane behavior. So we'll get back to these things later when we look at the stiffness matrix. And the laminated composite shells in FEM-Design use the first order shear deformation shell theory. And this is also known as the Reisner-Mindlin theory. And it's actually the same theory used for the regular orthotropic shells in FEM-Design. And it's important for the total deflections since the contribution of shear deformations can be significant, especially in a moderately thick shell, and especially in the case of a laminated composite shell, where the shear correction factors for transverse shear stiffness have an even greater role in the calculation procedure to get the appropriate displacements and stresses. So for a CLT panel specifically, this is important to simulate the rolling shear effect. So also as a rule of thumb when it comes to the geometry limitations, the calculation method is mainly valid in the following range, where the thickness of a laminated composite shell should be somewhere in the range of 1 and 10% of the average span length. So here we can see a plate that spans 4 meters. So the thickness here should be between 40 and 400 millimeters. That should cover most common applications. It's not an exact critical limit, but it can be a good rule of thumb to keep in mind. All right, so here in the middle, we have the new stiffness matrix. So it's the exact same size as before, so the laminated shells are compatible with the other objects in FEM-Design, but it contains this new submatrix B over here and here to achieve the coupling effect or the eccentricity part for non-symmetric panels. Okay. And in this equation that you might be familiar with, we have the force vector on the left side here. We have our specific bending moments, our normal forces, and our shear forces. And in the stiffness matrix, we have the bending part, the membrane part, and the shear part, and the new coupling part here. Then we have the strain vector here with our curvatures, our mid-plane strains, and our transverse shear strains. So enough of that. Let's look at an example showing the differences between an orthotropic plate and a laminated shell. Okay, so here we have two timber plates. Let's look at the properties of them. Okay, so they are the regular orthotropic shells. And we also have a new button down here called display stiffness. It's new for the timber plate tool. And here we can see the different parts of the stiffness matrix. So the D, A, and S, and the B part here. And for orthotropic shells, it is always 0. Okay, so what happens when we apply a load like this? We can look at the displacements here, and we get an in-plane displacement like this, no surprise. Okay, because an orthotropic shell cannot be asymmetrical in the cross-section, okay? But if we go to other plates we have here, and look at the properties of them, and the stiffness is non-zero here, okay? So we have an asymmetrical cross-section, and we load them the same way, but we get this kind of crazy behavior. So we have just the stiff direction indicates the arrow here. So that's the reason for the different behavior, okay? All right. So it's time to familiarize ourselves with the new interface over here. So yeah, let's see. Let's have a closer look. Yeah, so the new CLT module is included in the existing timber plate and timber wall tools, which we have here and here. So let's go into the settings of the timber plate. And we saw this box before, but we have a new drop-down list here, so we can choose a mechanical model, which is not the orthotropic shell, but the cross-laminated timber, and also a third option called general laminated composite. So this is for general materials, but we'll focus on cross-laminated timber today. Okay, so here's a handful of options right away, but we'll start by creating a new panel. We can use an existing one as a base and click new here. So here we have the panel definition dialog, and we get an overview over here. We can name it to webinar or something today, and we have our layers over here. So it's top-down order. If I hover the mouse over the layer here, you can see that it is marked with yellow in the top spreadsheet. So here I can change any parameter, and it's updated visually here. I can change the angle if I so choose. All right. And I can create a new layer by clicking that cell, and up pops this dialog, which is the same familiar material dialog as for beams. And we instantly get all relevant material properties if I choose from this, and it fills out in here. Okay, so the mechanical properties, which are the stiffnesses, Poisson ratio, shear moduli, and the density. So we also had a drop-down list here with the limit stresses. So we can take a closer look at them just to see how they are defined, okay? So looking at one plank of one layer in the panel, we can see that we have the bending strength along and across the grain. We have a tensile strength along the grain and perpendicular to the grain, compressive strength, and then we have the in-plane shear strength, transverse shear strength, and rolling shear strength. And then the last one is the torsional strength at a glued contact surface. Okay, so all of them are characteristic values, and all of this is, of course, also in the manual. All right, so what do we have more here? We have the KDEF values, which are the deformation factor from Eurocode. And we have them for service class 1, 2, and 3. So we can change these and see what happens. Then we have the stiffness reduction factors, and they're quite useful. So if the CLT producer gives these reduction factors based on test results or considering experimental formulas. So yeah, we'll also look at how these affect the stiffness matrix. So yeah, we had the one called drilling in some literature, R33, and this affects the torsional stiffness, which is connected to this strain over here, which is the torsional stiffness. Okay, so the membrane factor, this one, is related to the in-plane shear stiffness, R66, and then we have the shear factors over here, and they affect the out-of-plane shear stiffness. Right. Okay, so there's also some bonus info in the bottom right area showing total thickness and total surface weight. Okay, so I will go back to mechanical properties, maybe choose 40 millimeters for that one and click OK. All right, so then we have these parameters we saw earlier. Eurocode material partial factor, gamma M, from the national annex. Then we have the system factor, which is the K-sys. And this is really not necessary to change since the Eurocode 5 methodology is based on beam theory. So we can keep cases to 1 when using the CLT module here. Then we have the service class option here. So as you saw previously, we changed them inside here, and so they affect the KDIF factors over here now. Okay, but here we can choose different KDIF factors for different load combination types. So keep that in mind. Over here we have for different service classes, but over here we have for different load combination types. Then we have the shear coupling checkbox here. Consider shear coupling between layers, and the option here for no glue at narrow sides. So we'll look at examples for those now. Okay, let me open up a file here called EY, because this setting here called no glue at narrow sides, it's actually the same as setting the stiffness in Y direction to 0. So here we have EY 0, and then we have EY to not 0 here. And what happens when we load this? We're looking at the shear force tau xy here. Now we get no shear force in this panel with EY equals 0. So if I change this setting to no glue at narrow sides and run the analysis here, yeah, we get the same results. Okay, so to continue, we need to start looking at the new laminated shell stress results, which we have over here. And here's a classic way to view stress results like we did like this. Let's open it again. And you choose your stress result here, and we see them plotted like this, for example. Okay. But we're going to open up the detailed stress results now. So we click the magnifying glass over here, and we choose a panel, and we choose some point on the panel. And then we're presented with these 5 stress components and their distribution along the cross section of the point we selected. So we have our normal stresses, sigma x and sigma y, and then our 3 shear stresses here. So there's also a geometry figure of our plate, and we can also see in the title which plate is being used at what point. And which load combination. And the closest node with coordinates, the node number, panel type, and total thickness. So now we're ready to look at the shear coupling example, because we're going to look at these figures, okay? So let's open up the shear coupling example. Okay, so here we have 2 plates again, and one with the shear coupling on, and one with shear coupling off. So we have this effect. The shear forces are transferred in the layers here, and not in this one. So if we go into the detailed result, we can choose this predefined point here. And actually we can arrange them so we have them side by side here. like this. Okay. So if we're just focusing on tau xy here, you can see a linear shear stress distribution. And actually for tau xz here, we can get this classic parabolic shape in the transverse shear stress. So whereas if we compare it to the plate without shear coupling here, we don't have this linear stress along the height of the cross section. Instead, we get this pattern in each and every layer. So we can clearly see the difference in behavior between these two settings. Okay. So there's a whole lot of stresses, and finding the maximum stresses from components on the shell can be quite time consuming, especially if we have a complex structure and many load combinations. So now we're going to look at some tools that can help us out in finding maximum stresses. So let's open up a plate example here. And we're going to start out by showing a result from the maximum of load combinations. So it's this group over here, maximum of load combinations. And here we're looking at the laminated shell stresses, and we're looking at the, it doesn't matter which result we're looking at actually, but we have the sigma x belonging to the maximal tau xy. But we're going into the detailed stresses here. So to see the stress searching tools. So I'm going to use this result point again, okay? And up here we have some options to choose our plate, and we can select a coordinate system also. So we have a local coordinate system for the shell, and then we have local coordinate systems for each layer also. And we can select to view the stresses in any of these local coordinate systems. So here, 1 and 2, third layer, and they switch, okay? So 6 and 7 are have the same coordinate system, and they have the same coordinate system as the shell local system like this. So it was only 3 and 5 that was perpendicular to this in this case. All right, and then we have the load combinations or maximum load combinations over here. And then we can choose components. So this is one of the tools I want to show you now. So for maximum results like this, there are plenty of different maximum criteria available, and they can be categorized into 3 groups. So the first one is the all components maximum. So this one we're looking at now, all components plus. So this is searching through the load combinations that we have, component by component, and it gives us the largest positive value of each stress component along all the layers in the selected point. We can therefore see which load combination each component result belongs to. So here we have for sigma x P1 and sigma y also. Then we have one called ULS NY and a P5 and a P4 here. So potentially there could be 5 different load cases or load combinations here. Okay, so then we have category number 2, and that is the all layer maximum by stress type. So for example, all layer sigma x plus. So this searches for the combination that gives the largest positive x direction normal stress, the sigma x, along all the layers at the selected point. So this criteria displays results from only that one load combination. And the other ones belong to that maximum result, okay? Then we have group 3. and that's the layer maximum by stress type. So this searches for the combination resulting in the largest positive sigma x in the second layer at the selected point, if we choose 2-layer sigma x plus, like that, right? So it's the largest positive sigma x in the second layer at the selected point, okay? And another option is to query a detailed result without defining an exact point on it. So it's only available for maximum type results. The maximum criteria are the same as for the point-based detailed results, except that in this case, the searching is not limited to one node. The program checks all nodes on the shell according to the selected criteria. So we'll see how that works. We are in the maximum combinations result. So we have this button number 4 called select laminated shell. So we don't need to select anything else but just this panel, okay? So using this together with the all components maximum is excellent to see the overall maximum stresses on the shell, considering all nodes and all combinations simultaneously. Okay, so now we'll look at the basics of the design procedures of a CLT panel in FEM-Design. So we're going to open up a small box example here. Okay, we have 4 walls and some openings and a plate on top, and then we have some loads here, 3 load cases like that, and we have them in a load combination. Okay, so let's run a design and see what checks are made here. So we go into the timber design tab, and there's a new button over here, a new option for CLT panels. Okay, and then we can run design calculations based on our load combination. Okay, so then we can check our utilization rates. We see this one blinking over here. So let's go into the detailed utilization results for this wall. Okay, and it looks similar with this geometry figure and with some interesting nodes pointed out here with their numbers and coordinates. Then we get some panel properties, nice and tidy, tables here. And then we have our first design checks over here, okay? So all of the given checking equations are relevant in any layer of the CLT panel. Therefore, the equations are checked in every layer of every panel. And here we have the Eurocode design criteria with respective references here. So we have tension and bending in chapter 623, Eurocode 5, and compression and bending, and so on. But as we can see here, the stresses need to be separated like this. So how is that done? I can show you here. All right, here we go. And here is how the separation of compressive or tensile and bending stresses are done in one layer, okay? And that's to fulfill these equations to be able to calculate them like this. Okay, then we have the shear stresses. So let's refresh our memories with another image here. Okay, so the first one here, the tau xy, is the shear stress that could come from in-plane shear force, nxy, or torsional moments, mxy. So let's look at how that is configured like that, okay? Then we have the tau xz from transverse shear force parallel to grain direction, like that. And then we have the last one, the rolling shear over here, okay? And then the next design criteria doesn't have a Eurocode reference. So this is where we have extended the checking procedure outside of the regular standard. So the reason for this is, as previously mentioned, that CLT is not fully covered in today's Eurocode 5. It's not an individual material and it's not fully standardized. So that's why we have additional optional checks, which are a basic conservative strength of material checks. We can explain them quickly. Yeah, the interaction check according to these formulas will be performed in several points along the thickness of one layer to get the most unfavorable situation. So the first one here, that's checking of the resultant shear stress in the grain direction. Second one is relevant if there is rolling shear stress and tensile normal stress perpendicular to the grain direction. And the third one is if there's rolling shear and compressive normal stress perpendicular to the grain direction. And we can choose whether to include these in the design check if we go to the calculation parameters for our object here. Okay, so I'll check this button over here, calculation parameter, and select my wall, okay? And then I can uncheck this box. So we exclude it from the result here. I had to recheck the wall, and then we'll scroll over here and we have excluded those results from the report. So you may have noticed that there was another option here in the calculation parameters, and that's the torsional check. Okay, so that's only active if the shear coupling between layers and no glue at narrow sides option is adjusted. So it's a shear check at a glued contact surface from rolling shear and torsion between layers. So let's have a look at a wall which is compatible with that. This wall over here. If we go into the properties, then we can see we have shear coupling and no glue at narrow sides. Okay, so if we check this box here and go into the detailed result here, then we can use this go to button and go to the torsion chapter. So it's the last one here. And yeah, if there is no glue at the narrow sides of the planks, there would be an additional torsional effect in the glued surface between the adjacent layers, which could cause a failure. So that's why we have that check here. Okay. And then we have the buckling check. So there is no obvious buckling check information related to CLT panels in Eurocode 5. And that's probably one of the reasons why no other software offers this feature apart from FEM-Design. So following the basic rules of Eurocode regarding the reduction factor method, we have a new and unique calculation engine for dealing with CLT buckling in any direction. So the basics of it are actually quite simple. Yeah, we need to perform the following check here. We need to reduce the compressive strength, this one, with this factor Kc. So the other main principle is stress separation, like we talked about earlier for the design checks. So in an individual layer, this trapezoidal stress distribution is separated into a compression part and a bending part, layer by layer individually, as always. So with this stress separation method, the buckling check fits into the Eurocode 5 methodology, and the relative slenderness is defined in a general way. So in order to calculate this formula, we need Kc. So we need to calculate the relative slenderness. So we need this and this and this and this. And yeah, there's of course a lot more calculations and advanced algorithms going on in the background, but we can see here that we need to define a beta C and our effective buckling length beta for that matter. Okay, so let's go into the calculation parameters again here and check this wall, and we have the buckling options over here. So here we can see the beta C is 0.2 by default. And beta C is a straightness parameter, and 0.2 is the default value because that's on the conservative side, since again, no value for CLT is specified in the Eurocode. Other handbooks suggest other values, which is why this is an adjustable parameter. Okay, so we also have this R value. It's an input reduction factor that's usually between 0.67 and 0.84. So it's also a parameter since it's not completely clarified in the standard for a CLT panel. And another unique aspect of the method implemented in FEM-Design is the fact that we don't need to have our buckling direction in the grain direction. We can have an arbitrary buckling length direction. Okay, so I'll show you that. We set the buckling length as we always do in FEM-Design for shells with this tool. And here I can choose a user-defined direction. I select the shell and a direction like this and an area like this, okay? So here we can actually have a buckling length direction that is not in the grain direction. So we can check that again, that wall like that. Now we can go into the detailed results here. And over on the far right here, we should have a buckling check, okay? So here we can follow the calculations, which are again quite unique because we can have the buckling direction in any direction in relation to the grain direction. So that's a unique application and extension of the Eurocode buckling check for CLT panels. Okay, so that's about it, I think. Just want to show you a few last things. We have a Wiki page, which you can reach either by this address, or if you're in FEM-Design, you can just click the question mark over here and you get to the Wiki page. Then, yeah, we have the user manual links over here and the other manuals over there. Okay, so at the bottom here, we can download the cross-laminated composite shell theory. So the manual for the CLT module, which contains a lot of in-depth information, of course, and interesting verification examples at the end here. And you could also download the verification examples and follow along, okay? And our website, strusoft.com, if I can spell it. Here we go. If you would like to apply for a trial, you can click here and get started now. So if you would like to try FEM-Design, or you can write that you're interested in a trial in the CLT module, and you can try it out. All right. So that's about it for the presentation. Let's see if we have any questions. Zoltan, are there anything that you need to explain further?
Okay, can you hear me?
Yes, can hear you.
Okay, so there was a question about how about the deformation check. So during the homogenization of the stiffness matrix, we can consider the K-def deformation factor for the shear and Young's modulus. Shear modulus and elastic modulus of the different layer properties. So at the end of the calculation, when we have the deflections, we can quite easily to calculate the different deflection by the characteristic and the quasi-permanent serviceability limit state. And can you hear me, Joachim?
Yes,
So there
I can
was
hear you.
there were a lot of questions about how can the users, the attendees, reach the recorded webinar. So it will be uploaded to our YouTube channel, right?
Yes, it probably will, but you can also see it through the GoToWebinar page if you'd like to. Just use the same link as you got to come here today, and you will see a recording there, I think. Okay, so nothing else, Sultan?
I think I tried to answer the questions during your presentation, but if somebody would like to ask a specific question about this module, maybe we can wait a few minutes, because now I can see we just have some additional question above this module right now. Okay, are you agree with this?
Yeah,
Okay.
absolutely.
Okay, so it's there were some few questions about the deformation check for the K-def value. So I would like to answer those questions. So there was a question about how to consider the long-term K-def, I mean the deformation factor, and the instantaneous deformation during the calculation. Should we run the model twice or something like that? So the answer is that by the panel properties, the user should adjust the different K-def deformation factor by the different limit states. So we can check and we can set the ULS and the SLS, the three SLS combination deformation factors. And in the background, according to the type of the load combination, we choose the proper deformation factor in the back calculation of the program. And finally, when the user check the different load combinations, they get the proper stiffness, I mean the deflection results according to the reduced modulus, I mean moduli with the K-def, with the relevant K-def factors. So the answer is that no, the user should run the calculation just once, and in the background we consider the relevant K-def factor for the adjusted type of the load combination. There was another question according to why we get different material stiffness values by the orthotropic model and the CLT model. So the short answer is that it's a quite different mechanical model in the background. So an orthotropic shell, it has a quite different material stiffness matrix compared to the laminated shell mechanical model. So this is the difference between the mechanical model. The laminated shell model is a much more complicated model with a lot of back calculation and pre-calculation to gain the stiffness matrix.
Okay, great. Were there any more questions that popped up?
No, I think we tried to answer all of the questions which arose. So I think we can close the session maybe.
Okay. Yeah, great. Perfect. And if you have any more questions, you can just contact us, email us, and we'll try to answer them. And thank you very much, Zoltan, for answering all the questions and everything. And thank you for attending. So see you next time. Bye.
Bye-bye.